Have you ever really stopped and wondered what's going on inside a model like ChatGPT? I mean, it feels like actual magic, right? But it's not. It's this massive, fascinating, and kind of messy engineering process. Today, we're going to break that all down, how these things are really built from just a chaotic soup of internet data into a genuinely helpful AI assistant.
So let's pull back the curtain on the quote-unquote magic. We're going to look at the real deal engineering behind it all. We're talking the raw data, the training, the alignment process, and yeah, the staggering costs involved. Let's dive in.
At their very core, these incredibly complex systems are built around one surprisingly simple idea. They're called autoregressive language models, which I know is a super fancy way of saying their one and only job is to predict the very next word in a sentence. And this is so important to remember. Everything we're about to see, all the petabytes of data, the millions of dollars in compute, it's all just to make the model exceptionally good at this one single task. That's it. That's the secret sauce.
Okay, so let's get into the first major phase, pre-training. The best way to think about this is like we're sending the model to the world's largest, messiest library to read literally everything ever written. The goal? To learn the fundamental patterns of human language. But right away, you hit a really basic problem. How do you even feed text into a machine? I mean, if you break it down by word, the model totally breaks when it sees a typo or a new word it's never seen. But if you do it by individual characters, the sentences become way, way too long for the model to handle efficiently. So the really clever solution here is something called byte-pair encoding. You start with just individual characters. Then the algorithm finds the most common pair, like T and H, and merges them into a new single unit, TH. And you just repeat this process over and over, building up this smart vocabulary of common word pieces. That way, a new word like tokenizer can just be seen as token and izer. It's super efficient and really flexible. So what does the model actually read to learn all this stuff? Well, the raw material is a giant crawl of the internet. And when I say giant, I mean it. We're talking 1 petabyte of data. That is an unimaginably massive and incredibly messy pile of text to start with. And you obviously can't just feed that raw junk straight to the model. It has to go through this industrial-scale cleaning pipeline. First, you gotta rip the plain text out of all that messy HTML code. Then, you filter out all the harmful stuff and junk. After that, you deduplicate everything to get rid of the same sentences and website headers that appear over and over. And finally, you classify the data. Is it code? Is it from a book? And you decide to give more weight to the high-quality stuff. So, how do we even know if all this training is actually working? Well, we can measure its confusion score, or what researchers call perplexity. Basically, it just measures how surprised or confused the model is about what the next word should be. So, a lower score is better. It means the model is more confident and less confused. And the progress on this front has been absolutely incredible. Back in 2017, a model might have been juggling like 70 different possibilities for the next word. By 2023, that number dropped to less than 10. The models have become so much less confused about how human language works. Okay, so now we have this incredibly knowledgeable base model. It's basically an autocomplete on steroids. But how do we turn that into a useful, helpful AI assistant that you can actually talk to? Well, that all happens in phase 2, post-training. And this slide right here perfectly shows the difference. If you ask a pre-trained model to explain the moon landing to a kid, it might just complete your sentence with another similar question it's all online somewhere. But a post-trained model actually understands the instruction and gives a really helpful answer. One is just a completion engine, the other is a tutor. This whole alignment process, turning the completion engine into a helpful assistant, it happens in 2 key steps. First, there's supervised fine-tuning, which is all about teaching the model the format of a good answer. And second, there's preference tuning, which is where we teach the model to develop good taste by showing it which of 2 answers humans actually like better. Now, what's really important to get here is that this fine-tuning step, it's not about teaching the model new facts. All the knowledge is already in there from the pre-training phase. This is purely about teaching it the style of conversation, how to follow an instruction and give an answer in a helpful way, all based on these high-quality examples written by people. All right, the next step is direct preference optimization, and this is really the key to making the model's answers more helpful and harmless. It's pretty simple, actually. The model rates two different answers to a prompt, a human labeler comes in and picks the better one, and then the model gets trained to be just a little bit more likely to say the preferred answer next time. It's a really direct way to get the model aligned with what we humans want. So let's talk about the engine that's been driving all this progress. It's the shocking, almost unbelievable power of scale. And this is where we get into the truly mind-bending numbers behind these models.
In traditional machine learning, you're always worried about something called overfitting, making your model too big or too complex for the data you have. But with LLMs, the exact opposite is true. The research is crystal clear. Making the models bigger and just feeding them more data keeps making them better. The performance just goes up and up.
In fact, this relationship is so predictable that researchers have even figured out rules for it. The famous chinchilla rule basically found that for the most efficient training, you need about 20 tokens of data for every single parameter in your model. This lets teams perfectly balance their model size and their dataset size to get the most bang for their buck.
Okay, so with all that in mind, let's ground this in reality. Let's look at the actual, real numbers for training a top-tier, state-of-the-art model, something like Meta's Llama 3. The scale here is, well, it's staggering. First up, the data. After all that cleaning and filtering we talked about, the final training dataset had 15 times trillion tokens of text. To put that in perspective, that's thousands of times larger than the entire English Wikipedia. Next, the compute time. How long did it take to process all that data? About 26 million GPU hours. That's the equivalent of nearly 3,000 years of nonstop computation on a single top-of-the-line AI chip. And finally, the cost, the price tag. Just to rent that much computer time, not even counting salaries or anything else, would cost over $52 million for one single training run. So this recipe, more data, more compute, bigger models, it has been unbelievably effective. But it leads to this really fascinating and very real question for the future of AI. What happens when we've read the whole internet? What happens when we just run out of high-quality human data to learn from? That, right there, is the next great challenge.